Hello everybody, welcome into another lesson. So today we are going to talk about segments, rays, and distance. So let's start out here. Once again, we have a line. You can call this line AC because the line runs through points A and C, and of course every point between A and C, and every point to the left of A, and every point to the right of C. A line has no end. It just goes on infinitely in both directions. So that's a line. Now, I think that one was pretty simple. So what if I chopped off the end and I have a starting point at A, right? I've made the starting point at A and it continues on. But we have a starting point. It only goes on infinitely in one direction. This is called a ray. So this would be considered ray AC because it has a starting point of A and it goes on infinitely through point C and beyond point C. So of course we know we've seen a line before. The denotation for a line, you would put the little line symbol above AB to denote line AB, but if it's a ray, you only draw basically a small ray. That's how you would denote ray AB, is with a very small ray above it, with a arrow pointing in one direction. That would be ray AB. Or actually, this would probably be more accurate to say ray AC, since it runs through point C. B lies between A and C, obviously. Now, lines, it doesn't matter which point comes first, but with a ray, when you denote a ray, the very first letter must denote the starting point of said ray. And we could still make this a whole solid line because let's just say we take the line, we start at A, we make A our starting point and go through C and beyond. We don't worry about what's to the left of A, that's still a ray. We can still denote ray AC from this line. Or you can also do what's called an opposite ray. You could do an opposite ray where you have CA. This time C would be your starting point, and it would keep going to the left towards A and everything to the left of A. So that would be ray CA if you started at C and kept going further left past A. So you can pick out rays apart on lines too. It does work that way. What else here? We could also have, okay, let's say we have ray BA, and ray BC are opposite rays. These are opposite rays. Why are they opposite rays? Well, that's going to be because they both have the same start points of B. You notice B is the first letter on the ray denotation, but BA starts at B and it keeps going further left past A, because this tells you it goes infinitely past A. And then ray BC starts at point B and then it keeps going infinitely past C. So they're opposite rays because they have the same starting point, and the starting point lies in between points A and C, so those would be considered opposite rays. So okay, we have now dealt with rays. Our little ray of sunshine. Haha. Little joke there. Okay. Now, what I have here is what's called a line segment. This is a line segment, or simply just a segment. So a segment ends in both directions. It starts at a point and ends at a point. So as we know, a line has no beginning and no end. It goes on infinitely in both directions. A ray starts at one point but keeps going infinitely in one direction, while a line segment starts at a point and actually ends at a point. So you can say you have the whole segment AC. A line segment is denoted by the letters with a simple bar above it. A simple bar above the letters denotes a line segment. You have AC. You could say also you have line segment AB, because it could start at A, end at B. Or you could say you have segment BC. And you, just like we did with rays, you could still pick these out of a line, or you could pick segments out of a ray also. As long as you know your starting point and your end point for the segment, that's a line segment. So basically the breakdown of this is you have the line, which is kind of the master. You have a ray, which is a subpart of a line, because it starts at one point on the line as its end point and keeps going infinitely in one direction. And then a line segment, you can argue, is also a subpart of a line, or even a subpart of a ray, because it starts at one point and ends at a point. So those are line segments. Okay, so let's get into a little bit of let's do a little bit here with some number lines. Alright, what do we got here? -4, -3, -2, -1. We got 0. We got 1. This is definitely going to have to be extended a little bit here. We have 2. We have 3. Then we have 4. Okay. So, we have a number line here from -4 to 4. We can assign certain points here, which are basically kind of like coordinates, but only in one dimension. I have point J at -3. I have K at 0. I have L at 2. Whoops, K is at 0. L is at 2. Then I have M at 4. Alright, so I've assigned points. I've assigned certain points on the number line as denoted by a capital letter. Let me make the dots on each of these here. So, let's say here we have a line, right? We do got a line, but on this line there are segments, are there not? You have a line segment between J and K, starts at J, ends at K. Then you have K and L, that's a line segment, which start at K, end at L. Then you have a line segment from L to M, starts at L, ends at M. You could also have JL, starts at J, ends at L. You could have KM, starts at K, ends at M. Or you could have all the way from J to M, starts at J, ends at M. Those are all perfect examples of the line segments that exist here. Well, you can actually find the length itself. You can find the length of segments. So, let's say I wanted to find the length of segments, which this is going to be a little bit different, because when you're finding the length of a segment, you don't put the bar above it. You just simply put the two letters, JK. Alright? How you find the length of a segment is you take the absolute value of the second coordinate, which would be k, minus your first one, which would be -3. 0 minus -3, that's 0 plus 3. That would equal 3. So the length of segment JK is equal to 3. If I just had a bar over it, that would simply mean line segment. But if I want to find the length of that segment, the distance between the 2 points, the length, I don't put a bar over the 2 letters, if that makes sense. Let's do these all. What if I did KL? What if I wanted to do KL? Okay, so I'll take the absolute value of the second coordinate, which is L. I'll take 2 minus K, which is 0, which would give me the absolute value of 2, which is nothing more than 2. Alright, then what if I wanted to find LM? Well, I can also do that. I would take the second coordinate, the absolute value of the second coordinate of 4, minus the first one of L, which would be 2. Well, the absolute value of 4 minus 2 is also 2. So all these here represent various lengths of the segments. That's the length, that's the distance between the 2 points. That's what the length of the segment is equal to. Now, rays, you can't have lengths because it goes infinitely in one direction. Lines, you definitely can't have lengths. They go infinitely in both directions. But line segments, you can actually assign a length to. You can find the length because it starts at a point and ends at a point. It doesn't go on infinitely. So that is a good thing to know. And this is actually going to tie in to our very first postulate I'm about to give you. So, what is a postulate? You may wonder. We're going to throw a few definitions in. Postulate are statements that are accepted as true without proof. So, a postulate is a statement that we just accept as true without having to prove. And a lot of the times postulates are so blatantly obvious that you really don't need to prove them. So when we do proofs, we don't have to ever prove postulates. So that's one less thing for us to prove in this course. And we can use postulates in our proofs. So once we've learned them, we can use them. Now, there is something else here. Postulates are also called axioms. That's another thing. You may have also seen the term axioms in previous courses. That's another term for postulates. An axiom's a postulate. Now, a theorem, on the other hand, short for now, we'll go into it more later. Statements that must be proven. So, theorems are statements that must be proven. Those are what we're going to spend our time proving in this course. Now, you're going to use, of course, you'll be given some information at the beginning of the proof. You can use what's given to you. You can use postulates. You can use definitions. And if you've learned past theorems and proven those, you can use the past theorems that you've learned and proved to prove new theorems. So, that's theorems. But for now, for today, we only have 2 postulates I'm going to give you. This is called, the first one is called the ruler postulate. We have here the ruler postulate. All right. Let's see. Part 1 of this postulate states the points on a line can be paired with any real numbers. I'm just going to abbreviate numbers here with the symbol. With any real numbers in such a way that any 2 points I'm going to abbreviate PTS. Points will abbreviate PTS. Makes life a lot easier. Can have coordinates. I'll just call them chords, short for coordinates, 0 and 1. So part 1 of the ruler postulate here states that the points on a line can be paired with any real numbers in such a way that any 2 points can have coordinates 0 and 1. If we look at our diagram here, that's exactly what we've done. We have points on this line, don't we? We have assigned them real number values. J is -3, K is 0, L is 2, M is 4. So this is actual demonstration of the ruler postulate part 1 at work. We've paired the points on the line with real number values. So if anyone's writing this down or taking notes on part 1 of the ruler postulate, I'll pause for a minute here. Let me just pause for a minute. Give it another minute or so, then I'm going to move on to part 2. Okay, I think that's enough time for part 1. We're going to move on to part 2, which is a little bit shorter than this one. Alright, so part 2 of the ruler postulate states that once a coordinate, I'm just going to abbreviate a chord system. You're going to see I use a lot of abbreviations in this course. It's going to save you a lot of writing. Even in your proofs, you can use abbreviations. That does help you. Once a coordinate system has been chosen, the distance between the 2 coordinates, just say chords, is equal to the absolute, I guess it's not a little bit shorter, the absolute value of the difference of their coordinates. Alright, so part 2 of the ruler postulate states that once a coordinate system has been chosen, such as what we got here, the distance between two coordinates is equal to the absolute value of the difference of their coordinates. So we demonstrated that already when we found the length of JK, of KL, and LM. So yes, we've seen the ruler postulate at work on both parts here, of both parts of the ruler postulate. And in all honesty, if I want to find the length of JK, it doesn't matter if I start with J, then subtract the coordinate of K, or start with K, then subtract the coordinate of J. Because it's the absolute value. It's going to give you the same result. And if you think about it, it's the absolute value because you're never going to get a negative length. You just aren't. So that's why it'll be the absolute value, because lengths are always positive. Okay. I have one more postulate here to go over. This one might appear, once we talk about it, it's going to be obvious. This next one is called the segment addition. I'm going to abbreviate addition as ADD period. Postulate I'll abbreviate POST period, so I don't have to keep writing that word out. This is going to be called the segment addition postulate, which states that if B is between A and C, then AB plus BC equals AC. Okay, so basically the idea of the segment addition postulate is you have 3 points. You have points A, B, and C. A at one end of starts the segment, C's at the other end of the segment, but in between points A and C you have B somewhere between points A and C on the segment. The idea is that you could add up the length of segment AB plus a length of segment BC and get the length of the whole segment AC. That's how the segment addition postulate works. So let's demonstrate that with this number line here with some real life examples. We're going to keep this number line. So once again here, okay, let's do JK again. I'm going to find the length of JK. So to do that, I'm going to take the absolute value of the coordinate of J minus the coordinate of K. So -3 minus 0. Well, that's equal to the absolute value of -3, which just simply equals 3. Then let's say I want to find the length of KL. Let's go ahead and do all that here. KL, that's going to be equal to the absolute value of 0 minus 2, which would give me the absolute value of -2, which would simply give me 2. Now, the idea is here, let's see, let's find LM, because I kind of want to go on with this one. We have LM. To find the distance of that, the length of that, you would take 2 minus 4. The absolute value of 2 minus 4 also gives you the absolute value of -2, which gives you 2. Okay, so what if here, now that I have everything, I found the value of each individual segment, all right? What if I'm asked to find JL? So here's the segment addition postulate at work. I'm going to find the length of segment JL. Well, isn't it true that K is in the middle of JL? That point, well, it's not exactly in the middle, but it's in between JL. That's what really matters. The idea of the segment addition postulate is here, I could take the length of segment JK plus the length of segment KL, and that'll give me the length of JL. So if I stick in the values of JK, I would do 3 plus KL, which is 2, which means the length of JL would equal 5. 3 plus 2 is 5, so the length of segment JL is 5. That is the segment addition postulate at work for you. Let's do a few more examples here. Now, what if I'm asked to find Km? This time I'm tasked with finding the length of Km. Well, I can use the segment addition postulate to do that, because isn't point L somewhere between K and M? All I would have to do is take the length of segment KL plus the length of segment LM. That would give me the entire length of KM. So let's stick in the values here. KL, the length of that was equal to 2, plus the length of LM also equal to 2. Well, 2 plus 2 last time I checked was 4, so KM, the length of KM is equal to 4. Alright, so we found the length of KM. Now there is just one more I'd like to find. What if we are asked to find the length of JM? We're going to find the length of the entire segment of JM. Well, we know in between JM we have segments JK, segments KL, and segments LM. To find the whole JM, we could take the sum of 1, 2, 3 segments and put them together. So that's going to be the sum of the length of segment JK plus the length of segment KL plus the length of segment LM. So yes, if you're wondering, with the segment addition postulate, you can add more than 2 segments. As long as all those segments lie in between the start point and the end point, you could have infinite segments. You could add them all together and get the length of the segment. But this time we only have 3 segments to add to get the length of the entire segment. So stick in the length of JK, which was 3, plus the length of KL, which was 2, plus the length of LM, which is also 2. So 3 plus 2 is 5, plus 2 is 7. So the length of segment JM is going to be equal to 7. So by using the segment addition postulate, we can determine that the length of segment JM is equal to 7. Alright, there's still a little more. So those weren't too bad. The Rule Postulate and the segment addition postulate. The Rule Postulate you'll use a little bit in this course, but the segment addition postulate you'll use a lot. So if you haven't taken notes, I would highly encourage you to, because we do use a lot. So let's see. What does it mean for congruent? The next term I'm going to throw out is congruent. What does it mean if something is congruent? Objects have the same size and shape. So that's another term you'll need to know, is about congruent. So let's say I had 2 of these whiteboards side by side, the exact same ones. You could say they're congruent because they're the same objects, they have the same size and the same shape. So those would be congruent whiteboards. You could also say that their sizes are equal. Congruent and equal basically being the same thing. In fact, especially here in geometry, you're going to hear those terms used interchangeably and thrown around a lot. So congruent is basically another word for equal. So keep that in mind. So let's talk about congruent line segments here. So let's say I give you a line segment here, DE, right? We've determined we got DE. That's going to be equal to, we'll say 3 inches. I know this is a lot bigger than 3 inches. Clearly, that's about 6 inches, probably even 9 inches, but just go with it here, okay? Then I'm going to draw another segment, which I had FG. This is also a 3-inch segment. These would be called congruent segments because they're the same size. They're both 3 inches. So if they're the same size, if they're congruent, there's 2 ways to write this. You can start here with segment DE is congruent. So here's the congruent symbol, is congruent to segment FG. So this is how we're going to say segment DE is congruent to segment FG. It looks like an equal sign with a tilde above the equal sign. That's what the congruent symbol is. Another way you can write this is you can write it as simply the lengths of them. You can say DE equals FG. That's another way you can say it. And as I said, congruent and equal basically mean the same thing. So you're going to see those used interchangeably throughout geometry. So we can say line segment DE is congruent to line segment FG, or we can say length DE is equal to length FG. I mean, you could say either one. It wouldn't really matter. All right. Couple more here. Let's say AC, right in the middle I'll put B. So I have line segment AC, okay? Right smack dab in the middle I have point B. Well, if B's in the middle of the segment, we can call B is the midpoint, which I'm going to abbreviate it mid-PT period, of segment AC. So we could say B is the midpoint of segment AC if it's smack dab in the middle. And if the segment is equal, in other words, if the two segments equal each other, if you have a point right in the middle, if you have a midpoint of that segment, it splits these segments into 2 equal parts. So you can say line segment AB is congruent to line segment BC. It'll split it into 2 congruent segments. Or you could say length AB is equal to length BC. You can write this either way. They both mean the same thing. But that's what a midpoint does, splits one segment into 2 equal segments. And then last one we want to talk about is the bisector of a segment. We will talk about segment bisectors. That's the last thing for today's lesson. So let's see here. Let's draw a nice plane. Let's draw a plane first. That's actually going to be more helpful today to draw the plane first. We're going to call this plane plane X. That's plane X. Why don't we draw it a little bit lower? That might help us. There's a reason I'm doing this. I need to teach you about segment bisectors. Alright, so here's plane X. Now, since this is solid here, this is going to be point Q. This will be point P. Since this is solid, this will be a line above the plane. I know the drawings can get a bit funky. Okay. See, ends in B, ends in A. And then what's the other one here? I'm just trying to draw this right. Which way does it go? Alright, so I have our nice figure here. So we have plane X. Above plane X, we have line segment QP or PQ. You can call it either way. A segment, it doesn't really matter which coordinate comes first because they both start and end, so it doesn't matter. But then running from the outside of plane X, starting from the outside, you have line segment AB, and then you have line L. Well, what we can say here, we have a couple bisectors. We have a couple segment bisectors. So we're going to talk about what segment bisectors are. Segment bisectors. Or segment bisector. We'll just say that so you know what the term is. So you think about it. To bisect something is also to split it into two equal parts. Right? Kind of brings back the whole midpoint thing. So a segment bisector can be another line segment, it can be a ray, it can be a line, or it could even be a plane that bisects a line segment right at its midpoint. So let's start with the line segment here, coming from above the plane to line segment AB. We can argue that line segment PQ bisects line segment AB. Because look at it here, you have line segment AB, right, starting from outside the plane going through it. And then you have right above it, you have line segment PQ that touches line segment AB right in the middle of it. Since it touches it right in the middle, right at the segment's midpoint of P, this can be considered a segment bisector. So line segment PQ is a segment bisector of line segment AB. Okay. What else? You notice here we have line L. Well, line L intersects line segment AB right at its midpoint of P, right? I know this doesn't look exactly mid, but for all intents and purposes of this one, P is at the midpoint of line segment AB. You have line L that goes at an angle like that. You can also argue that L bisects line segment AB. So If you just see a lowercase letter, that means a whole line. That's only the case with lines, again, like from yesterday's lesson. So line L bisects line segment AB. And here we actually have a plane. We have entirely plane X bisecting at point P. You notice everything's outside the plane up until it reaches point P, then it comes inside the plane, right? That's the dotted line to the left of point P for both of these, for both the line segment and the line, means it's outside the plane. But as soon as you hit point P at the midpoint of line segment AB, everything runs through the plane of line L and line segment AB. So you could actually argue that plane X bisects line segment AB. So that's how that would work. Plane X also bisects line segment AB at point P. So yes, those are really all the definitions today. So let's do a few exercises here. I'll feel a lot better if we do a few exercises. We're going to apply what we've learned today with some true or false statements again. We already did some distance problems. I'm not going to do more of those. I'm sure you're all quite fine with simple arithmetic by now. I don't doubt that. Okay, let's see here. We have, what do we got here? We have line KT. So this is going to be an interesting diagram. Then through here we just have line segment HL. And to top it off, H and T are connected. The midpoint is M. Not the midpoint, but that's where the line segment and the line intersect, is at point M. Okay? Let's see. So line segment HL and line KT intersect at M. Actually, it says at the midpoint of HL. So now we got a class. So we have line segment HL and line KT intersect at the midpoint of HL. So that means now we have to classify a few statements as true and false. How about this one? Line segment LM is congruent to line segment MH. This is a statement we need to classify as true or false. Is line segment LM congruent to MH? Well, the line segment and the line intersect, right, at the midpoint of HL. Well, they intersect at point M, do they not? That tells you that M is the midpoint of line segment HL. So that means at the midpoint, it divides segment HL into two congruent segments of MH and LM. So yes, this is actually a true statement. Line segment LM is congruent to line segment MH. That's actually a very true statement. Now, what's the next statement say? Km must equal mt. Alright, so this statement is that Km must equal mt. Well, we know that the line segment HL in the line KT intersect at the midpoint of line segment HL, but notice with the statement you're given, it doesn't say anything about whether it's at the midpoint or not of line KT. Does it not? We don't know if it's at the midpoint of line. Well, it wouldn't be at the midpoint now, would it? Lines go on infinitely. So, we don't know anything about line KT, so it may be true, it may not be true. If we don't know, there's not enough information given, and it's saying it must, it's saying it has to be equal, we're going to say this statement's false. We don't know anything about line KT, and it's saying it must equal MT, so that's a false statement right there, because we don't really know one way or another. Alright, how about this? Line segment MT bisects LH. Alright, so now we're given that line segment MT bisects segment LH. Well, again, the segment and the line, they intersect right at the midpoint of HL, it says, right? M is at the midpoint of HL. Well, this is definitely line segment MT, is it not? M is attached to the midpoint of HL. Line segment MT definitely bisects line segment LH, so by judging by the diagram and the statements we're given, this is actually a very true statement. Line segment MT does bisect line segment HL. Alright, what do we got next? Let's see. We have line KT is a bisector of line segment LH. So this statement is that line KT is a bisector of line segment LH. Well, it says that lines KT and line segment HL, they intersect at the midpoint of HL. Well, line KT runs through the midpoint of HL at point M. So yes, this is true. Line KT is a bisector of the segment LH. This is actually a true statement. So you see, these aren't your typical math problems. This is really getting you to look at stuff and be observant. Alright. Ray MT and TM are opposite, I'm just going to abbreviate opposite rays. So let's take a look at this here. Ray MT and TM are opposite rays. Well, I'm going to say yes because it starts at M, keeps going past T all the way up into the sky infinitely. And then TM, it starts at T, keeps going down all the way past M, all the way down into the ground. So this would also be a true statement. These are opposite rays. So yes, it's true. Rays MT and TM are opposite rays. Okay, what about the next one? Well, let's see here. Now we also have, what about MT? Raise MT and raise MK are opposite rays. So we have ray MT, then we have ray MK. They both have the same starting point, but they're going in opposite directions. Yes, this is true. Those are opposite rays. Okay, what do we have here? Line LH is the same as line segment HL. So this is saying that the whole line LH would be the same as line segment HL. Well, we don't even really need to look at the diagram. We could tell right away this is a false statement, because segment HL literally means it starts at L, starts at H, ends at L, or vice versa. That's the entire line segment. L and H, the line LH covers not only those 2 points, but every point beyond those points. So clearly this is a false statement. Clearly that's false. Oh yeah, want to talk about something real quick here. I kind of made a blunder a couple problems ago when I said that rays MT and TM are opposite rays. I made a blunder. I'm man enough to admit it, and I apologize. Rays MT and TM are opposite rays. This is actually false. I'm going to tell you why. So, I'm not saying I'm always 100% right. I'm not perfect, but I'm man enough to admit when I'm wrong. But the first ray starts at M, goes through T and beyond. The second ray starts at T, goes through M and beyond. In order to be opposite rays, they must have the same starting point. These do not. Now, granted, they both have the same points on the rays, and they go in opposite directions, but that does not make them opposite rays. So that's actually a false statement, so forgive me for that. It dawned on me for a minute. Okay. Let's see. Ray KT is the same as ray KM. Alright, so this statement, ray KT is the same as ray KM, just the statement. Well, starts at K, ends at, and keeps going past T and beyond. And then we have ray KM, it still starts at K, right? But then it goes to M and beyond M. Well, point T is beyond M, and it keeps going even beyond T, so this is actually true. That's a true statement. It keeps going infinitely in the same direction as both points M and T, so that's actually a true statement. Now here's one. Line KT is the same as line KM. So line KT is the same as line KM. Well, both T and M lie on the same line, do they not? And it goes to all points beyond the endpoint, so this is actually true also. This is another true statement. Because M and T are on the line, so is K, and a line goes infinitely in all directions, in both directions, beyond all those points. So that's another true statement. Only got 5 more. We have line segment KT is the same as line segment KM. So now we're only talking about line segments at this point. It's saying that the line segment KT starting at K ending at T is the same as line segment KM starting at K ending at M. Clearly not, because M is between points K and T. Clearly this is a false statement. In order for the segments to be equal, they would have to have equal length, which we may not know the length of those segments, but very clearly they're not the same if M is between the whole thing. So that one's blatantly obvious. 4 more. Let's see. HM plus ML equal HL. So let's see. It's saying that length HM plus ML equal HL. Well, this is true by the segment addition postulate. They're both subsegments of the main segment HL, so this is actually a true statement. You just add their lengths together, you'll get the whole length of the entire segment. So that was a true statement. 3 more. How about length TM plus MH equal TH? Alright, so let's see. We have length TM plus MH equals TH. Well, they're not on the same segment, are they? They're on different lines or line segments. So this is false. This is false. In order for this statement to be true, they would have to be parts of the same line segment or the same line. So that's a false statement right there. Alright, T is between H and M. T is between H and M. That's false. T is definitely not between H and M because it's on an entirely different line. So, it's on an entirely different line. I'm going to say that's false. Now, M is between K and T. That's true. M is definitely between K and T because they're on the same segment. So that's all there really is to this lesson. The next lesson we are going to talk about angles. So we're going to have some fun with some angles. I hope everyone has a good night. Take care.